All right. Today, we are actually going to introduce the definite integral by looking at area under the curve problems. And the problems that we're going to look at today actually are very solvable to find the exact area under the curve because they are dealing with situations that either give us the areas of certain regions already computed, or actually are doable, with geometric formulas. So what we're going to kind of discuss here is what is a definite integral. So the definite integral, as opposed to an indefinite integral. So the integral that we just showed, where we procedurally computed the antiderivative, this is called a indefinite integral. And the integral that we are going to be computing, this definite integral, we just integrate for a part of the function. So we have the a and the b. So we can actually see that there's a function called f of x, which is actually speaking a derivative, and the antiderivative will actually kind of give us the area, and the a is the lower limit of integration. And the b is the upper limit of integration. A few other things that you should know. Areas that are below the x-axis are negative areas. And areas above count as positive. And geometrically speaking, we are taking the area between the curve and the x-axis. And I'll kind of say like cumulative area. Between curve and x-axis. So I think it is important to kind of know that definite integral and know its interpretation geometrically. So this definite integral would actually follow the picture really well. A few background knowledge that you will need for the problems from the days of geometry. You are going to actually see some pretty familiar shapes. So one of the formulas that you'll see are the rectangles. So this is the area equals length times width. You'll see triangles. So that's the area equals half base times height. We're actually going to see semicircles on many of our delta math examples. And this is pi r squared, but then you're putting it times a half for a semicircle. So these are some common geometric formulas that you'll need to know. And also the trapezoid, as we've kind of discussed before. So that's area equals 1/2 times B1 plus B2 times H. So that is all the geometry that you need to know. And what we are really going to be focusing on is actually looking at some problems with these areas and kind of breaking them into shapes. And if it's not for the integral notation, I actually could give these problems to one of my geometry students, and they could actually do them as kind of a combined area problem. All right, so for example 1 here, we are going to be looking at a type of problem that's called find integral from given areas. So the good news is that they actually already are computing the integrals for you, or parts of the areas for you. And we'll call this example 1. So this says the regions A, B, and C in the figure below are bounded by the graph of the function f and the x-axis. The area of region A is 5, the area of region B is 9, and the area of region C is 18. Compute the integral from -8 to 4. So I'm going to actually shade between the function and the x-axis. Coloring is not perfect, but that's okay. And it's saying, what is the value of the integral? So the area that's below the x-axis, it gives us that a is equal to 5. So I'm going to say that a is -5 because it is below. B is 9. And then C is below the x-axis again. So we're going to say -18. So we can actually say that the integral from -8 to 4 of f of x dx is equal to, and I'm just going to kind of call this capital A plus capital B plus capital C. And I'm just going to add up those areas. And I get 9 minus 5 minus 18. So you could go do that math in your head or go to a calculator. So let's see, that's going to be 4 minus 18, so that's going to be a -14. Let's see how that works. One of the things that's nice about Delta Math is it actually does show you what the positive and the negative area are. I will say what is kind of nice about their presentation is that they talk about that it is the areas, and that is, you know, kind of a good introductory problem because the areas are already given for you. Okay, the next problem we're going to do is compute the definite integral from a graph, level 1. And what's different about these problems is that we simply did not baby you and give you the areas, but you're going to be starting to compute areas of pretty familiar shapes. So the goal is that you want to turn this in from a calculus problem to a geometry problem. So we'll call this example 2. So we have a graph of a function that is shown below, and we are going to go from -9 to 1. And I'm just going to kind of trace the area that we need to find. And you can kind of break this in. Let's see, we got, you know, 2 trapezoids. So you could interpret this as 2 trapezoids, or you could interpret this as, you know, a rectangle and some triangles. I'm going to just do the two trapezoids. So I'm going to call this like region 1, and I'm going to call this region 2, or you could call them like A and B, you know, like they did on the previous one. I just like kind of just doing them by region. So the region 1 is 1/2, and you do need to find your, you know, B1 and B2. So let's see, this is going to be 2, and this is going to be 4, and my height is going to be 5. So it's going to be 1/2 times 2 plus 4 times 5. And I'm just going to find out what that total area is going to be. So let's see, half of 6 is 3. 3 times 5 is 15. You could always do the old school manual way of counting the rectangles too. And then for number 2, I'm going to actually count the units here. So I have 6, and I have 2 on top, and my height is 6. So let's see, I got half of 8, which is 4. 4 times 6 is 24. And then I'm just going to add those two areas up. And I have 15 plus 24 for a total of 39. So we did trapezoids. You could also, one thing that I kind of like about the way that Delta Math does this is it actually breaks it into smaller integrals. So if you are studying the solutions, you can actually break it into those smaller integrals and kind of break them into those problems, and they will actually help you with properties of integrals. So it's like taking the integral from like -9 to -7, and then from -7 to -5, and -5 to -1, and so on. And what they do is they actually just compute the 4 areas. So they actually, as kind of an alternative route, did the 2 rectangles and 2 triangles. Now, I would say that somebody who has, you know, kind of a time test, or wants to get the question in the fastest amount of time, you know, would actually look at it in terms of 2 trapezoids. So what matters on these type of problems is that you are backing them up with legitimate area formulas. All right, level 2. Level 2 still gives us pretty familiar shapes, but what we have kind of moved towards are above and below the x-axis. So I'm just going to go ahead and trace. So it's asking us in example 3 to find the area between the curve and the x-axis between -3 and 7. So I'm actually just going to kind of use a highlighter feature here. So here's -3, and here's 7. And if it helps, I'm just going to make the positive area green. So here's the curve, and we're pretty good until here for a positive area. And then the negative area we'll just kind of do in the red. And it gives us, I'll just kind of put it in highlighter mode. So it gives us that triangle below. And if we want to kind of get in the habit of using integral notation, we can, or you could kind of, for the purpose of this exercise, just do the numbers. So let's see, I'm going to call this 1, I'll call this 2, and then I'll call this part 3. So 1, if I want to do this as an integral, I could say that we're going from -3 to 2 of f of x dx. And this may feel a little tedious for you right now, but it's actually going to help you with property of integrals a little bit later. So one of the properties is that we can add up individual definite integrals to get, definite integrals over bigger ranges of area. And this is a trapezoid on its side. So let's see, we got a 4 and we got a 3. And then the height of the trapezoid is going to be 5. And its area, when we do that, let's see. So I got 1/2 of 4 plus 3 times 5. So 7 times 5 is 35, and half of that is 17.5. And you could even manually count and see if you're in the ballpark. Some people actually, they could actually do the rectangle and then just minus like the sliver of the triangle. So you do have some leeway on these problems as long as you are getting the correct areas and having the rationale. All right, region 2, this is the integral from 2 to 4 of f of x. And it's a nice triangle. So it's 1/2 times 2 times 3. So it's just going to give us an area of 3. And then the third region is the integral from 4 to 7. And for this one, we are in the negative space. So this is going to be 1/2 times 3. And then we're going down 3 below for the height. So let's see, 1/3 of -9 is just -3. Or let's see, 1/2 of -9. Actually, it could be -4.5. And then we can just add these up. So you got the positive area and the negative area. So that's part of what makes this a level 2. And we are at 16 even. And let's actually see how we did. What Delta Math actually did is they divided it into, they didn't do trapezoids. But I like, kind of doing those trapezoids because it really does speed up the process. And you can actually see that by turning it into a trapezoid, we were able to do it with fewer integrals, fewer area computations, and we got the same effectiveness of the answer. All right, our last example, we're going to kind of showcase a level 3. And level 3s are level 3s because they may have like the positive and negative areas, but they also have, things like semicircles or quarter circles and that type of stuff. So fortunately, we do know how to take the area of a complete circle. So here we're going from -1 to 9. And I'm just going to trace, so it is green, so it's positive. So I'm just going to kind of trace the curve from -1 to 9. And then I'm just going to color the areas. And actually, what is nice is it actually just gives us a big triangle and then a quarter circle to compute. And sometimes, you know, for those ones that kind of are reminiscent of like a circle, I even like to just call it a quarter circle and then add a quarter to the pi r squared. And it says, you know, write your answer in the simplest form. So first region is my quarter circle. And I'll get this back in red so we can see a little clearer. So this is the integral from -1 to 1 of f of x. And it's equal to a quarter circle. So this is a quarter pi r squared. And the radius, we'll just kind of say that the radius is equal to 2. So let's see, that's a quarter of 4. So that's just going to get us to pi. And we'll just keep it as pi for right now. And then the second area is going to be the integral from 1 to 9 of f of x dx. So this is going to get us to 1/2 times, and let's see, we got 8. And it's a triangle that is 1, 2, 3, 4, 5. So that's going to be 20. And we could even just write this as pi plus 20 units squared. And I believe that would be a pretty friendly format for delta math. So we'll write pi plus 20. And there we go. So they do like answers in terms of pi on some of those for the level 3s. So I wanted to kind of just show you one of each level so you could kind of see the escalation in difficulty. And fortunately, if you can decipher the upper and lower limits, so you are able, the main ideas that you should take away is that the integral is area of curve between a function and the x-axis. Upper and lower limits set the right and left boundaries. And with those two things, the good news is that you can break them into almost everyday geometry problems. So I could actually give literally this problem, and literally this problem does exist on the area, combined area problems in the geometry class. And the only thing different is that we had to use the integrals to actually come up, you know, with that problem.